Chapter 8, Non-Electrolyte Solutions, Section 8.8, Ideal Dilute Solutions and Henry's Law. Ideal dilute solutions, they are not ideal solutions. They are highly diluted solutions. For example, if the mole fraction of the solvent is 0.9999 and the mole fraction of the solute is only 0.0001, we have a nearly ideal dilute solution. Again, ideal dilute solutions are not ideal solutions. So if we have a two-component ideal dilute solution, let's say components A and B, the AB interaction, the A interaction, and the BB interaction are different. However, if you just study the solvent in the ideal dilute solution, the solvent still obeys Raoult's law, just because each solvent is pretty much surrounded by other solvent molecules. In this situation, 99.99% of the molecules that surround a specific solvent molecule are other solvent molecules. So again, 99.99 is almost pure. So that's why the solvent behaves like a pure solvent liquid. However, if you look at the solute in an ideal dilute solution, it does not obey Raoult's law at all, because think about it, now each solute is not surrounded by other solute molecules. Each solute molecule is surrounded by pretty much solvent molecules only. So the chemical environment of each solute molecule in an ideal dilute solution is completely different from a pure solute liquid. But still, we have a proportionality here. The partial pressure of the solute on top of the ideal dilute solution is proportional to the mole fraction of the solute in this ideal dilute solution. And why is that? Again, the partial pressure of the solute is proportional to the number of solute molecules on the surface. Only the surface molecules can evaporate. So that's why this P solute is proportional to the mole fraction of the solute molecules in the liquid, in the ideal dilute solution. But the proportionality is different. We have to define a different constant here. We cannot use the pressure of pure solute here. We have a different constant called Henry's constant. And right now we're looking at Henry's law. In the Henry's law, it states that the partial pressure of the solute is proportional to the mole fraction of the solute in the solution. The proportionality is called the Henry's constant, and the value of the Henry's constant depends on the identities of the solute and solvent. So for example, if the solute and solvent strongly attract each other, and then we'll have a smaller Henry's constant. But if the attraction between solute and solvent is much smaller than the attraction between solute molecules, well, then we have a large Henry's constant, because we have more solid molecules in the gas phase. So again, Henry's constant, denoted by this K sub H for the solute, depends on the identity of the solute and also the identity of the solvent. We really need to look at the interaction between the solute and solvent and see whether it's stronger or weaker than the interaction between two solute molecules. Again, when the solute is strongly attracted to the solvent, this Henry's constant is smaller than the vapor pressure of pure solute, because in this case the solute is stabilized by the surrounding solvent molecules. However, if there's not much attraction between the solute molecule and the surrounding solvent molecules, and then we will see a higher vapor pressure for the solute, and therefore a larger Henry's constant. Ideal dilute solutions, again, are highly diluted. Here's the example. If the mole fraction of the solvent is 0.9999 and the mole fraction of the solute is only 0.0001, we have a really good ideal dilute solution. Henry's law can be used to calculate the vapor pressure of the solute. In an ideal dilute solution, we have this equation. The partial pressure of the solute is equal to a constant times the mole fraction of the solute in the solution, and that constant is the Henry's constant. Again, Henry's constants depend on the identity of both the solute and the solvent in the solution. It also depends on temperature. Here's one example. Let's talk about the Henry's constant of a gas dissolved in a liquid. Usually this Henry's constant is significantly greater at a higher temperature because the entropy of the gas phase is much larger than the entropy of the liquid phase. And remember, dG is negative SdT plus VdP. So the gas phase is more favorable with lower molar Gibbs energy at higher temperatures than the liquid phase. All right, higher temperature gas phase is more favored, and it's hard to dissolve the gas in a liquid. Actually, this is why in a really hot summer day, the fish tend to be more sluggish, because in a hot summer day the water temperature is significantly higher than usual, and we have a very large Henry's constant over here. The oxygen pressure is roughly 0.2 bars, no matter the weather is warm or cold. So this is 0.2 over here, and in a hot summer day we have a large Henry's constant. Therefore, we have a smaller mole fraction of oxygen in water. So in water, we have less oxygen dissolved in water. Of course, we have also less nitrogen dissolved in water, but fish, I think, mostly need oxygen. And because in a hot summer day, this is still 0.2 bars, no change. This Henry's constant is larger at a higher temperature, and therefore we have a smaller mole fraction of oxygen in water, and fish does not get enough oxygen in a hot summer day, and they tend to be more sluggish. Again, we have this equation to be used to make predictions when this partial pressure of the solute, of the gaseous solute, is constant, and then this is smaller at higher temperatures, because when this is greater at higher temperature, we can rewrite this Henry's law to a slightly different equation. The mole fraction of the solute is equal to P of the solute over this Henry's constant. Again, a larger Henry's constant at a higher temperature results in a smaller mole fraction of the solute in the solution. Since the pressure of oxygen in air is constant, less oxygen can be dissolved in water in a hot day. And now we can look at the Henry's constant of oxygen in water at different temperatures. Alright, in a hot summer day, let's say 40 degrees Celsius, let's look at Henry's constant. Henry's constant is, let's look at this data point, it's about 70,000. In a cold day, 10 degrees Celsius, it's about 40,000. So between 10 degrees Celsius and 40 degrees Celsius, the Henry's constant is almost double. That means the mole fraction of oxygen in water is almost halved. Again, Henry's law applies to ideal dilute solutions. That means we need a very small mole fraction of the solute. Henry's constant is often expressed as pressure per mole fraction in atm or pressure per molar in atm per molar. So either way, you can, as long as you use the units consistently. This is just because actually the concentration of solute in a solution can sometimes be expressed as a mole fraction, sometimes be expressed as molar. Now let's look at one numerical example problem. 8.8.1. Calculate the mole fraction and also the concentration of oxygen in water at room temperature, assuming the water and air are at equilibrium. So really, I'm just saying the oxygen in air and the oxygen dissolved in water are at equilibrium. And then we can compute the mole fraction and concentration of the oxygen gas dissolved in water. First, the partial pressure of oxygen in air is roughly 0.2 atm. Alright, so we have this P of the solute is 0.2 atm. The solute is the oxygen gas in water. And this is equal to Henry's constant times the mole fraction. Where is the Henry's constant? It's right here. Over here, this Henry's constant is in the unit of atm per mole fraction. So it's 43,000 atm times x. We can easily compute x by using 0.2 over 43,000. We get 0.000047 as the mole fraction of oxygen in water. So in 1 mole of water, we have 0.000047 moles of oxygen being dissolved. Now let's look at the concentration of oxygen. Again, this is Henry's law, but in a different format. Over here, we have 0.2 atm times this Henry's constant in a different unit, atm per molar. So over here, we need to have concentration in molar. And then let's look up the Henry's constant in atm per molar. It's 770. So we have this number here, and then we do some calculations. C can be computed. It's 0.00026 molar. And because in 1 liter aqueous solution at room temperature, we have roughly 55 moles of water. So just imagine in 1 liter of water, we have 55 moles of water, and we have 0.00026 moles of oxygen. And then you can just use these two numbers, 55 moles of water, 0.00026 moles of oxygen. You can just simply compute its mole fraction. The mole fraction is roughly 0.00026 divided by 55, which is 0.000047 over here. Yeah, that's just the mole fraction of dissolved oxygen in water. Now let's talk about the physical meaning of these two numbers. Well, this number means if you have an oxygen pressure of 770 atm, and then you can dissolve 1 mole of oxygen in a liter of water. If hypothetically we can extend the behavior of the ideal dilute solution to such a high concentration. Again, this is a hypothetical analysis. All right, so we're assuming this oxygen in water still behaves like a ideal dilute solution under such a high pressure. Then you can achieve 1 molar concentration. Over here, what does this mean? Well, this means if you have a 1 atm pressure, let's say just 1 atm of oxygen above water, the mole fraction of oxygen is 1 divided by 4.3 times 10 to the power 4. Again, we're assuming the ideal dilute solution behavior.